In my last video, I went through the use of PixInsight to generate a background adjusted image using the dynamic background extraction tool. And I use this process for all of my images, be they narrowband or broadband. However, the next step I'm going to go through is a sharpening process that I use and apply to only the luminance images I collect. This is the deconvolution module. Now, what deconvolution does is it tries to correct the image for aberrations caused both by the optical train and by atmospheric turbulence. And as you can imagine, these types of corrections can also magnify the background noise levels. So before you can apply deconvolution, I have to generate some additional support images. The first is a Psf image, which is a point spread function. What this does is defines the ideal star image that you would expect from a star without any type of atmospheric distortion. And then the other two files are a deconvolution and a star mask. And what these do is prevent deconvolution from taking any noise it sees in the background and trying to correct it and generate more noise in the process. So now that I've described the basic steps we have to go through, let's actually go into PixInsight and apply them to my picture of the Rosette Nebula. So I've opened up my image of the Rosette Nebula, and you can see that it is still in a linear state by the green band that is on the identifier tab. And I'm going to now generate the Psf image, and you can do this in one of two different ways. I'm going to show you first a manual way to select stars to make the model, and then after that I'll show you that there is a script command which can do this automatically. So to go through the manual process, we go to Process, Image, and select the dynamic Psf module. And the screen opens. And what we would like to do now is select a number of stars. 20 is probably the minimum that I typically use. That will be used to generate the Psf model of the star. So in order to do this, what I do is I zoom in, and we do not want saturated stars. So if full saturation is a relative amplitude of 1.0, we'd like to pick stars that are somewhere between 0.2 and 0.8. And I'll show you how we can do this. So let's pick this star here. I click on it. You can see it's selected. And now here in the dynamic Psf module, you can see it's been populated with some data. And we go to A for amplitude, and you can see that the amplitude of the star is 0.08. So I said we want it between 0.2 and 0.8, so that's a little bit low. Could be used. Let's pick another one that looks a little bit more intense. Perhaps this star here. And you can see this one, the intensity is a little bit too high, 0.94. So we'll keep going around until we find a star that's suitable. So here's one that's good, 0.7138. So we would keep that, and what we could do is select these other two stars and use this red bar to delete them. Now you'll see that also has a designation of Moffat here, and that describes the distribution of the light coming onto the sensor. So the distribution of light on the star is neither truly Lorentzian or Gaussian, but rather follows this Moffat distribution. So we would like to limit our stars to those described by that Moffat distribution. So what I do now is I go around the image and I start selecting a number of different stars, and I'll get back to you in a second when we have enough to analyze. So I'm done with this star selection exercise, and you can see that I've selected stars all over the star field, about 70 in total. So what I'm going to do now is sort them to make sure I'm only using the most desirable stars for the image generation. So if we go down here to the sorting tab, we'll click that button, and first I'm going to do is sort them by amplitude. So we say OK. And if we go up here, amplitude is column A. And what I'm going to do is I'm going to take any stars that are below 0.2 and using this red delete button, delete them. Similarly, I'm going to go down to any values that are above 0.8 and delete those as well. Now I'm going to look at the actual star shapes, and you can see that they're all described as Moffat in distribution. We have no Lorentzian and no Gaussian distributions, and that's fine. And then finally, I'm going to go down and sort again, this time by the mean absolute difference, MAD. And here what I would like to do is see values that are below about 5 times 10 to the minus 3. And if you can see, actually, I will be getting rid of a number of values that are higher than that. And once again, we'll delete those. And what I'm left with is still larger than 20 samples to carry out the calculation. So I'm going to select all of these images. It's really important to select them. I forget to do this all the time. And now there's a small camera icon, and if I click on that, it generates our synthetic image up here. Let me blow this up. And this is a synthetic image of our star. So this is what we will be using in the deconvolution module. So let me just minimize that and show you another way that we can go about doing this. So a second easier way to do this is to select our image file and now go up to Script and Render and choose the Psf Image script. And once we have this, you can see that the amplitudes are already set default to values between 0.2 and 0.8, and it's going to generate a maximum number of 50 stars to sample and make an image. So we hit the evaluation button, and this is going to take a while to scan. So we'll get back to it once it's completed the process. So we're reaching the end of the analysis, and once we reach it, it actually gives us a projection of the distribution both in the x direction and y direction. And you can see that they overlay each other very nicely. So this is a spherical, pretty spherical star sampling that we've gotten. See 50 stars that are all Moffat were done with a MAD value of below 0.006. So we'll now hit the Create button. And you can see it now has generated an image file. So we'll just say OK. And if I blow this up to 3:1, you can see we have a very similar image to the one we generated earlier. So I'm just going to close out of our first one, and we're going to minimize this, and that is going to be the Psf image that I will use in deconvolution. So now I'm going to generate the first of two different masks. And this first one is going to be a star mask, which is best carried out on the unstretched image. So here's the unstretched image, and I'm going to go up to Process and Mask Generation and select Star Mask. And I generally leave these settings at their default positions. Here is the default, with the exception that I will check aggregate and binarize under the mask generation. Leave the smoothness at 16, and I leave the scale at 5. If we need to make the masks bigger, and when I mean bigger, I would like to have the masked image overlay all of this brightest stars here. So the masked stars should be slightly larger than those in the actual image. If I need to make those larger to ensure overlap, I can always increase the scale factor to 6 or 7. I've never really had to go to 7. I usually do 5 or 6. So once we have this set up, we take the triangle in the corner and pull it over our image file, and the computer starts generating the mask. So now you can see that we've reached the maximum point in extracting structures, and we've generated this new mask image. So to test this, what I will do is, first of all, increase the frame size. And then what I'm going to do is sort of blow this up so that we have a zoomed in view of these central stars. Now, in order to match this view with that in the image, I'm going to just take this tab from the star mask and lay it right on top of the ID tab for the image. So now these things should overlay. And if I put them over one another, I can go back to the image using the Control or Command page down. And you can see that our masked stars are a little bit blurred and slightly larger than the stars that they're going to be masking, which is exactly what we want. So I think this is a good mask. I'll just pull this off. And what I'm going to do, oops, this is the image file. So let's put that back. Take our star mask. And I'm going to take this and minimize it. And just put it up here with the Psf image. And close this out. And we are now ready to generate our last mask. The final supporting image I'm going to generate is a mask. And this is the Deconvolution Mask, which is probably the most complicated of the three. So the first thing we're going to do is take our image and we're going to stretch it. And now take our stretched image and make a clone by grabbing the identifier tab and pulling it over here. And let me just increase the size of this. So here is our clone. And what I'm going to do is grab the identifier and rename this as Decon_mask, just so we don't lose track of it, and say OK. Now what I'd like to do is turn this into a very high contrast mask. So to do that, we open up the screen transfer function again, and I'm going to reset this, hit the check mark, and select our mask. And now with the magnifier, I can actually increase the scale here. So I can grab this leftmost triangle, which is the black point, and slide it. And you can see we start to darken our background quite substantially. Now, what this eventually will do is be the mask to protect the background from the deconvolution module. So I don't want to slide this too far where we remove the nebulosity itself, or else we won't get any benefit of sharpening the finer structure in the nebula clouds. So we'll go back and forth with this a little bit. There we've darkened a lot of the background. We've let the nebulosity. So now I can zoom back out. And in a similar fashion, grab the white point slider and slide that to the left in order to enhance the brightness of the nebula and the stars. So once we've got this set up, not going to go too crazy with it. But now we need to render this mask non-linear before we can apply it. So to do that, I go over here to Process and down to Intensity Transformation, and we're going to open up the histogram transformation module. So to make this non-linear, let me just reset that. We're going to grab the triangle here from the corner of the screen transfer function, pull it down to the lower margin of the histogram transformation, and now grab the triangle from histogram transformation and drag it onto our mask. And you can see it goes almost completely white, and this is because essentially we've double stretched the image. So I can go up and reset the screen transfer function, and you can see now we've got our nice masked image. So let me just minimize histogram transformation for a second. And we could use this as is. What I usually do is want to blur this out a little bit. So I've made this image container here, process container, and in it I've got two different modules that'll execute. One is the morphological transformation, and I have this set to dilation as the operator with a size of 9. And what this will do is bloat out the stars just a little bit so that they're larger than the stars in our image. And then the second step is a convolution step. So this will cause a blur, and I set this to a standard deviation of 3.5. And you may have to play with this depending on your actual image. So I will close on to that. And now we take our mask, and I'm going to drag the triangle here. And what it should do is blur the image a little bit. And it has. So we're just going to close out of the process container. And now what I'm going to do is, you can see it's also brighten up the entire image. What I'm going to do is select this, and I am going to hit stretch, and once again play around a little bit with the darkness slider here, black point slider, to darken the background once again. So I've darkened that up. And similarly go back and try to brighten up the nebulosity just a little bit. So this doesn't look like a bad image. What I'd like to do is see how this looks. So we're going to put it, what I'm going to do is drag the tab over onto our image to apply this as a mask. And you can see it's there because the tab has gone brown. And now we can minimize our mask. Let's put that aside for the moment. And to actually see the applied mask, we go to mask. Well, first of all, we'll select the image. We'll go to mask and say show mask. And here you can see it. Red protects, so you can see that there's substantial red in the background. Now, just to see how well it's overlapping, I'm going to blow up. And what we can do is with Command K, we can apply or unapply the mask. So you can see basically that we're cufflering up the stars fairly well. I find it actually easier to invert this. So we go to mask and invert. And now when we show it, we can actually see how the mask is applied to the stars. And you can see that the red mask regions are a little bit larger than the stars themselves. So I think the blurring is working pretty well. So let's go invert this again so that the background is protected. And I'm going to just unshow the mask. Okay, so now we're ready to do our deconvolution. So to actually carry out the deconvolution, we're going to go to Process, Deconvolution, and execute the deconvolution module. So you can see that there's a number of different things we're going to have to set here. First thing I do is I increase my wavelet layers to 4. I've also been very successful in just leaving this set to the 2. And then here under PSF, we're going to go to External PSF. And what we're going to do is select, there's the PSF file that we generated before. We're going to leave the algorithm to regularize Richardson-Lucy. And usually what I do is I increase my iterations to 20. Next, we're going to go to de-ringing and open that up. We check it, open it up, and also check local de-ringing. And the support file for this will be our star mask. Okay. So now we're all set up and we're ready to actually take a look at this. Now, this is very CPU intensive. So what I tend to do is go up here to preview mode, and generate a preview. And here I'm going to generate it down here where we have a number of different stars, some nebulosity and some fine feature. And you know what? I'll do another preview somewhere else, maybe up here in this region. So that'll be preview number 2. So let's just take a look at preview number 1. And I'm going to blow this up a little bit so we can see what we're doing here. So you can see some of the finer structure in the nebulosity. You can see the stars that are a little blurred. And what we're going to do now is grab the triangle and we will apply it to the preview. And you can see with such a small size, it looks horrible. And this is what happens when our global dark on the D-ringing is set to the default of 0.1. It's really awful. Let me show you what happens when we take it all the way down to 0. So essentially shut it off. We go back, and once again, we will apply this. And it turns out you need to only do use very small values of the global dark D-ringing in order to control this D-ringing issue that we see here. So this is what happens with D-ringing switched off. We get these dark circles around our stars. So this is no good. So let's go move this value up to 0.002 instead. So let's reset and we'll try this again. And you can see now we still have D-ringing. It's quite a bit better. So I'm going to go back again and let's increase this to 0.004. So this is much better. There's not quite as much D-ringing. There's some modeling in the background that I really don't like. What I'd like to do is take a look at my mask again, make sure it's just properly applied, and it is. But if we go back and forth, you can see our bright stars have decreased quite a bit in size, and our nebulosity, some of these features have sharpened a little bit. So we don't want to go too haywire with this because it's a very subtle tool. I'm going to increase this again to 0.006. We'll see how that looks. So that looks much better. If we go back and forth, you can see once again, the shrinking of the star sizes. And at the same time, some of these dimmer stars that you see around here are actually brightening up a little bit. So this doesn't look too bad. There's still a little bit of that modeling in the background that I don't like. So to counter that, I'm going to increase the global brightening to 0.001. Let's see what that does. That does a nice job. You see now the background is largely unaffected. And we're still getting that subtle reduction in our star sizes without generating a lot of that background modeling. So that looks pretty good. You know what, we'll try 0.002. And literally I've spent hours on this. So that looks good. The background is really totally unaffected. And yet we're getting that enhancement and sharpening of the overall image. So I like this. I'm going to leave it there. Take a look at preview 2, and we're going to apply the same values to this and see if we get a similar effect. So that's complete. And once again, you can see a reduction in the bloating of some of the brighter stars, and some of the dimmer ones, we're seeing a small enhancement in the amplitude. So this looks really good. We'll go to the main image and get rid of our previews. And now we'll apply this to the main image. And this is going to take quite a bit of time. So we'll get back to it when it's complete. So now the deconvolution has been completed. We can zoom in on our image and take a look at before and after. And you can see we have quite a bit of star reduction that's occurred. So this isn't a bad change. What I will do is go to the identifier. Well, first we're going to remove the mask. So we'll go to mask, remove mask, and I'm going to save this as a new file. Save as. And what we'll do is behind DBE, just put down underscore DEC for deconvoluted, and we will save that. Okay, so we are done with deconvolution. We've got a slightly sharper image. And next thing we're going to do is take some of the noise out of the background.